stretching story because the feeling in conditions.
Good afternoon, everyone. We have listened to more than 10 presentations about soil and biological soil. I think it's time to look at something more complicated, biological soil. So today my topic is about how to develop SPSS framework to model the failure behavior of the slot. Consisted by frozen soil. And in terms of this, so we do the next slide.
Đúng ngược lại. Press down.
Soil-induced rock landslide now become more and more frequently reported in cold regions or in those seasonal regions. When the temperature rising up, the ice melting water in frozen soil, and there will be a generation of the exact polar pressure that will shorten the soil structure and lead to the failure. And this problem is much more complicated because compared to the problem that we discussed before about dry soil, in the soil, frozen soil now we have water, we have ice, and we have soil particles. So how considering the multi interaction in the frozen soil is a really challenging problem. To describe the behavior of frozen soil, that would be a really complicated custom model. And sorry for that. Right, so how are we going back?
Press down.
Okay, sorry about that. So here's the first challenge we need to address in order to model the failure behavior of frozen soil. So the next challenge is how can we find out in the mathematical framework to describe the whole process? Because in the frozen soil application, we have like four more degree of freedom, like how can we show the polar pressure, how can we find out for ice pressure, and how can we show temperature and heat conduction and whatever. And after we define these two stuff, we still need a numerical tool to solve all these kind of equations such that we can have the application to model the software algorithm. So let's first looking at the mathematical framework. As I said before, frozen soil is different from dry soil. For example, if we're looking at this RVE of frozen soil, you can see that in the soil we have four phases, like air phase, ice phase, and water phase, and soil phase, and soil particle, and they all have interactions with each other. For example, when the temperature is up, the ice phase may melt into water. When the temperature drops down, the water may form into ice. And during this process, there will be a really complicated work to the behavior of the soil as well, and then further influence on the shear stress behavior. So, in order to describe this whole system, we need this RVE, and depending on this RVE, we can find out the basic definition of different phases like partial density or partial stress and something, whatever here. And then we substitute all of this into the mass conservation equation, force balance equation, and energy balance equation. And then we can finally develop this sort of the fully coupled TXM model with thermal, mechanical, and hydromechanical model. In here you can see we have exactly this governing equation for solid particle, which will have another four additional formations. For example, change of velocity, and the change of the ice pressure, and change of polar pressure, and temperature, and so on. So by showing these four additional formulations, so the additional degree of freedom compared to the dry soil can be addressed. And the next step is to how can we find out the stress relationship so that we can describe the failure behavior or the behavior of the frozen soil. So we need a custom model. When we talk about custom model for those multi-phase material like unsaturated soil or frozen soil, the first key stuff or the primary point is that how can we define the developed stress? And this used to be a really intensive by topic before. For example, in the developed stress definition in saturated soil, and there have been a lot of approach to define developed stress, and different developed stress concepts have different advantage and disadvantage. The same concept or same situation can apply to frozen soil as well. And the debate for this efficient selection will become less intensive until Husky derived the efficient stress using the work input concept. In this case, we also apply the same concept to derive the efficient stress formulation for frozen soil as well. You can see that we selected the RVE, and the total work input to the RVE of the soil can group up these four parts, like mechanical part, suction training part, and suction part, and other health by other effects. So based on this work input, we can find out several work conjugate relations. For example, the work conjugate relation between the suction and the degree of saturation, work conjugate between the stress and the strain, and based on this work conjugate stress relationship, we can define the stress. How we define the stress here, and after the definition of the stress, the next step is to figure out the cost model or the surface. Here, we selected the KSM model as the base model to expand it to the model for frozen soil. So the question would be, how can we include the influence of ice phase on the mechanical or volumetric behavior of frozen soil? Here we selected the quiet organic suction as a primary variable. The quiet organic suction is very similar with the mixed suction. In frozen soil, the quiet organic suction was defined as the difference between the pore ice pressure and water pressure. So we selected as the primary variable here, so that we can define this, the loading graph which is used to describe how the shear strain change when the suction change, or when the temperature drop down, when the soil is freezing. There will be an increase of the organic suction, so there will be an increase of the shear strain as well, in terms of the expansion of the new surface. And the volumetric behavior also can be considered in our model. For example, when the soil is freezing, there will be an increase in the suction. At the same time, because when the water was boiled to ice, there will be an expansion in the soil structure. And this expansion actually will lead to some plastic volumetric deformation. And this will further lead to the shrinkage of the pre-cancer suppressor. This actually is the reality. For example, when the soil is undergo freezing, and there will be some expansion in the volume. And then after that, if the soil is undergo thawing, and the ice melts into water, and actually the soils become much softer. This can be reflected by the shrinkage of the suppressor in this pre-saturated state. And this is just a very simple example to show you how our model can capture very complex mechanical behavior of the frozen soil. So the next step is when we have the evaluation stress and we have the constitutive relationship, the next step, how can we define ice content or water content change? Here we're using the salt water replacing curve here in terms of this suction here. So when the temperature change, we will have the suction change as well, and we have the degree of saturation change that we can reflect the ice content change. At the same time, we can use this degree of saturation, or let's say the ice content, how it's going to be for a new change. And that's how we formulate this constitutive model. So the next step to verify the performance of the model here. In this case, in this talk today, I'm using two experiments to verify this model. For example, the first one is the traction test that conducted by Lai in China. They have the frozen sample and freezing to a certain degree, like -4 degrees, and then combine sample by different combining stress, and then do a traction test. You can see that our model actually captures very well the stress relationship as well the water behavior. And the next experiment was done by Xu, also in China. They have the soil sample taken from the field and freezing it to different temperature, -10. You can see that when the temperature dropping more, there will be more ice falls in the soil sample, and you can see the shear strain increase. And what will actually capture the this trend. At the same time, when the soil will undergo more freezing, actually it will become more dense as such. So you can see that there will be more diagenetic behavior when the soil is subject to the abstraction test. So in this figure here, I will also capture the this trend. So this is the constant model. So the next step after we have this constant model, and the next step is to incorporate this model into the framework that we did discuss before, and then forming the 3D THM model. The next step is to using the numerical method to show the whole system, such that we can model the failure behavior of frozen soil. In this case, I'm using the MathGrid method, so I'm not going that much detail because before we have 4 methods why I'm discussing the SPS method here. So this method is a MathGrid method, so the concept domain actually is described design into a single set of articles, and each article carrying all the information and the information at each point here actually can be approximated by using a kind of function into this term. And this function here can be replaced by any function of any Q quantity. Like, for example, the total pressure or other variables also can be approximated by this function here. And then we also can define first derivative or second derivative. And this formulation, after the divided formulation, you can apply it directly to this. We design the Gaussian equation that we established before, so that to show the THM process. So the next step after THM framework is to verify the performance of the model. So in here I selected this non-thermal consolidation problem to verify the performance of the framework. So in this case here we have a fully saturated soil problem was subject to a substrate loading, and this will be similar with the boundary consolidation problem. And then we increase the temperature from the top surface. And so in this problem here, the soil will undergo two processes. One is the consolidation, another one is the thermal expansion. So we can see here our model actually captures well the heat conduction and the temperature change. At the same time, the deformation at these different locations here also very nice capture. For example, at the first stage, the soil was undergo consolidation and settlement was observed, and after that, the heat still continued to infiltrate in the soil from such that we can see the expansion of the soil from here. That means our model, captures well the thermal and hydraulic and chemical process. So in the next slide, I'm going to show you how our model can apply to model the field application. In here, we have a slot here. It's covered by one layer of the soil, frozen soil, and the temperature is -5 degrees. And then we're raising up the temperature from the outside so that we can trigger the melting of the ice or the soil of the frozen soil and leading to the failure process. So in here, I'm showing you the model result. In this animation is showing you how we capture the temperature. Then the temperature will be raising up from the outer experiment and it will gradually transfer into the slot and leading to the increase of temperature in the slot. And the increase in the temperature will lead to the ice melt into water. You can see that when the ice melt into water, the water will shift down to the interface between the unfrozen and frozen interface. And the increase of the sorry about that. So here, you can see when the temperature increases, ice melts into water, and the water will dissipate down and infiltration down and accumulate on the interface because the frozen soil below is impermeable. So the accumulation of the water here will lead to the stress reduction of the soil so that the slot just cannot maintain the stabilization area. And this was automatically captured and no predefined things no predefined sliding surface. All of this was automatically captured. And this slide shows you some quantity like how we monitor the ice pressure change from this location, how the water pressure change in this location, and how we capture the dynamic change of the sediment from the top surface here, which means that this model still can be applied to a wide range of geotechnical problems related to frozen soil. So here's the conclusion. In this talk, we propose a constant model with a one conjugate value graph, and this can be used to capture